Well, good morning, everyone. Let's start with today's lecture. There are some questions by a student from like the example that we solved in lecture 22. Let me share my screen. All right, this example. Maybe I can turn off my camera so you can just focus on the screen. This is the example from lecture 22, and I thought you guys could solve it on your own, which most of you maybe did. There are some questions I quickly continues its solution. Just to refresh your mind, let's move back a few slides. This is from lecture 22. This is where we started talking about kinetics of rigid bodies. And we said for rigid bodies, instead of Newton's law, which is for particles, we will use Euler's law. And Euler's law are very similar to Newton's law. The first law is telling us that sum of all the forces is going to be equal to m a bar. A bar here is the acceleration of the center of mass, center of gravity. And like always, similar to Newton's law, if you have this one, you can break it down to sum of the forces in x is equal to m a bar x, sum of the forces in y equal to m a bar y, or any other direction. It doesn't have to be x and y, it can be t and n, or anything else. And then about the moment, because unlike a particle, now the rigid body has a size and it can rotate. Since it can rotate, then there are these forces, they might create a moment or a torque about g, right? Forces multiplied by their distance gives us m. And sum of all these m about point g is equal to I bar of alpha. And I bar is moment of inertia about the center. And then we said sometimes we need to calculate the moment about another point other than center of gravity, like point P. In that case, the formula changed to the first part is similar. Sum of the moment about point P is I bar alpha, still it is I bar. And then there is an extra term, M A bar, whatever A bar is, multiplied by D. And again, you can break it down to X and Y. And a big mistake that I've seen a lot is that the student take the moment about point P and they write down is equal to IP alpha, which is not correct. The only scenario that it is true is when P is fixed to the ground as a joint, like everything is rotating about point P, which was this scenario. In this scenario, the rigid body is fixed at point O, and you are allowed to take the moment about point O and write down IO alpha, okay, which is an important equation. And we proved why it is true because of the parallel axis theorem, right? Which we know this is because of transform of axis, transformation of axis, which we talk about it in lecture, I believe 21 or maybe 20. So, and then we start solving this problem to explain the physics. Like always, we need to understand what's going on. There is this link and you can visualize it's being joined to the wall or to the ceiling, but we are looking at, let's say, a vertical view of this link. So it means we have gravity, there is weight. And the question is telling us if we release it from the horizontal position, right? You release it from the horizontal position. We want to know what it says, okay, the forces at A at joint A, because maybe later we want to design a bearing and we need to know the forces at A. At two moments, when we just release it, when it is horizontal, and when it reaches to the vertical position. So we could have solved it just for these two positions, but instead we are trying to solve it for a general case as like angle theta. Then later, if we have the general formula, of course, we can put theta equal to 0 here, and we can put theta equal to pi over 2. Always, I tend to write the angle in radian, because sometimes if theta is not inside the cosine or sine, then it matters to be in radian. All right. But when it is inside the cosine or sine, it doesn't matter, because your calculator will take care of it. So always with rigid body, we said we draw two diagrams. One is the free body diagrams, the one that you see it on the left. So this one, we'll call it a free body diagram, right? F, B, D. Or the force diagram. We will write down all the forces that logically exist. We don't care about their direction because we don't know if they are positive or negative. First of all, we need to select an axis. It's okay to select horizontal and vertical axes as X and Y, or we can, like in this scenario, if you recall, we decided that maybe X to be along the link and Y being perpendicular to the link is easier maybe. But one suggestion that I have, try to solve the same problem using horizontal and vertical axes to see if you can get the same answer, which you should. That's going to be a good practice, in fact. So we have AX and AY, and as you can see, the direction, I just assume they are positive. If we get at the end of negative number, that's okay, because it's just the direction is going to be changed, but the magnitude will be the same. And weight is a vertical force, mg. We break it down to its component, mg sine theta and mg cosine theta. As simple as that. This is the free body diagram. And then the diagram on the right is the kinetic diagram, or acceleration, let's call it, diagram. Over here, we draw all possible acceleration that exist. First of all, we need to be careful that this thing is rotating. So since it's rotating, there must be an alpha. And then we look at the motion. Obviously, this rigid body has a circular motion. Remember, we had three categories of motion: pure translation, pure rotation, and combination of these two. In this scenario, we are dealing with a case when we have pure rotation because A is a fixed point. So if I have a rotation, so immediately I should realize that I should have an AT and AN. Because I'm writing about point G, I write them down as A bar T and A bar N. The formula, we know A bar, like AN, I'm going to write it down here again to remind you, AN is always R omega squared, and AT is R alpha. So we draw their direction. We try to do our best to draw them in the right direction. So obviously this thing is falling down. So it makes sense that alpha is rotating clockwise. Therefore, AT seems to be in this direction that I draw, and AN is always going toward the center. The link, we assume its length is L. So this distance then is going to be L over 2. Our R is going to be L over 2. So we have three equations, or two. One is for sigma m about point A, which we did. According to Euler law, because it's rotate about a fixed point, I can write some of the moment about point A is IA alpha, and then the rest is obvious, right? So I have this mg sine theta, which its moment is 0, mg cosine theta multiplied by L over 2. And IA, we'll look up the table and we will find out for a link in one end, the formula is 1 over 3 ml squared. Link, a rectangular shape, and a disk or a circle, and a ring. These are important objects which you should memorize their moment of inertia. You're going to use them a lot in future and in this course. So rather than always looking up the table, if you solve enough problems, naturally you will remember those. And be careful for a link, I bar, I'm going to write it down here, is 1 over 12 m L squared, right? These two are different. One is about its center of gravity and one is about one end, which using the parallel theorem or transform of axis would get the same answer. But when you solve a problem, do not rush it to just put here 1 over 12, because then all your calculation, which will be based on alpha, will be wrong. Okay, so, and then we are going to get to the other two equations that we have, or other equation that we have, which is for the forces. Always with Euler law, we have some of the M equation, right? And then some of the force equation, M A bar, and this one I bar alpha. Or other equation, like here in this scenario, we will use IA alpha and we write equation about point A. So if I look at my A bar, I can notice that I have omega here. So I need to figure out the speed of this link. So I have some formula for omega. So do you guys remember how we can calculate omega? So remember, we have alpha. We successfully found alpha, the angular acceleration. We want to know what's the speed of this link based on theta. Anybody can tell me how we can calculate omega? You can unmute yourself or just type in the chat. Okay, that's good. One accent. Yeah, exactly. Achilles got it right. Omega d omega alpha d theta. If you recall, I told you before in earlier chapter that this is an important formula. So we can use, let me go to the next page. So we can write down the relation that we know exists between omega, theta, and alpha. And in fact, this is an important equation because it relates three important parameters in a system: angular velocity, omega, angular acceleration, alpha, and position, theta. All right. And without considering time, like in this question, we don't care about time. So why we confuse ourselves adding another new parameter like time here? We just deal with this here. Let's see how it can work out. So omega, we don't know, and the omega is the integral. Alpha, we just found it. Let's move back one slide. It is 3 over 2 G over L cosine theta. This is alpha, and then d theta. Obviously, we don't want any d omega and d theta, so why not we integral? So we integral, right? Everything starts from 0. Like here, I have d omega. My speed starts from 0. And I want to know at any random theta, what is the new omega? You can call it omega 1, omega 2, or whatever, like in general omega. And then over here, I have theta. So Again, let's solve it for general case. We know it to start from 0, and let's say it gets to a general theta. Quickly, let's do the integral. I'm sure it's easy for you. The first side will be 1/2 omega squared. And then the second side, so all of those are constant. So it's going to be 3/2 G/L and sine theta. So we successfully found the speed at any theta. Omega squared is equal to 3GL sine theta. So I want you to do a quick check here. Let's move back to the slide that we just saw, previous one. So when I release this link from the horizontal position, okay, forget about the notes. For now, just please pay attention to my question because it's important. Imagine that we release this link from the horizontal position. We keep it with our finger and then we release it. At the very first moment that we release it, so obviously a speed is 0, right? Because we just release it. It's more like a car that wants to start. No speed, so omega is 0. What about alpha? So I'm going to write it down here at theta equal to 0. So what happened? We release it, right? We release it. Omega, we know intuitively is 0. What about alpha? Should it be 0 also when we release it? What do you think? Let me check. So some people say yes, some people say no. Rocky says no, Josh, yes. Akhilesh agreed that it is yes. It will be at its max. That's true. All right, so it's an important thing to think about it carefully because again, many problems that in future or in this course that you solve, like a mistake like that can lead to wrong calculations. When we release it, omega is obviously 0, but alpha is not 0 because if alpha is 0, what is going to push these things? Like you are sitting in your car is at rest, its speed is 0. You want to speed up, right? You want to start speeding up. So it means in the next 0.001 second, your car has some speed, but at 0, its speed is 0. However, since your speed is changing, it means there is an acceleration. That's why when you sit in your car and you want to start, you put your foot on the gas to accelerate the car. And here the same. Here there is no, of course, gas or something. However, there is this weight mg, right? The mg is trying to move everything. So there is acceleration. Intuitively, something that you need to carefully think about it. Okay, at the release position, there is an alpha, but omega is 0. So always remember, velocity, either angular or linear, can be 0, but acceleration can be non-zero. Okay, so let me quickly check the question in the chat. Yep, and I see you guys also got to the formula. This one is this one is a good thing to check your formula. Look at this formula that you have for alpha. Put theta equal to 0. You will get alpha equal to how much? 3.2 G/L. Right? So you see alpha is not 0. Let's check omega. if theta is 0, then you will find omega is 0, right? So formula is correct, and intuitively things seems to be right. And Rocky and Josh, they are correct. At the beginning, the acceleration is the maximum. And also, you know, when theta is 0, cosine theta is 1, right? And it is maximum as well, and everything makes sense. Okay. So keeping that in mind, let's continue solving the problem. We successfully found omega. We have alpha and we have omega. It means, let's move back to the slide here. It means our diagram here now, we know everything about this diagram, the acceleration diagram. We know alpha, we know omega. So we should be good to use the Euler formula. Let's use the Euler formula. So Euler formula says sum of the forces is equal to ma bar. Okay, and you can simply break it down to sum of the formula in x is equal to m a bar x. Again, it can be t or it can be n. I just show it by x, but maybe we should have shown it by t and n, but doesn't matter. It's just a letter. So what do I have in x direction? Let's move back to the diagram again. Okay. Whatever I have in x direction, the forces, I have ax, which is positive. I have mg sine theta, which is again positive. They are all in x direction, right? This is what I have for my forces, one side of the equation. And what do I have for acceleration? I have this a bar n, which according to my coordinate, it is negative, right? It is in the opposite direction, and you need to be careful about that. So let me draw my coordinate again, just to remind ourselves what's going on here. So this is our x, and this is our y coordinate, and we have to follow this positive direction that we choose. Okay, so let's write them down, and please check my calculation to make sure that I'm not wrong. So what do we have? We said we have ax, right? And then we have mg sine theta. They're all positive. This is on the left, right of the equation. And what do we have on the right? We have m L over 2 omega squared. This is all we have. All I did, I just write whatever we have here, whatever we see according to their direction. Nothing new, nothing unusual, right? Whatever we see here. Let's substitute omega squared there and simplify things a little bit. So we will get ax plus mg sine theta equal to minus m. I can get rid of that L, so it will be 3 mg squared sine theta, right? You can cancel L, and then this is what we will get. And from here, I'm gonna have ax equal to, so it goes to the other side, it's gonna be minus 5 over 2 mg sine theta. So this is the reaction for ax, right? At any angle theta. Let's do the same for the sum of the forces in y direction is equal to m A bar y. So again, whatever I see on the diagram, so I have AY. Let's move back one slide. So in Y direction, let's take a look together. I have AY is positive. Then I have mg cosine theta. It is in the opposite direction of Y direction. And then acceleration seems to be positive. It is in the direction of Y. Okay, so again, whatever we will see in the Y direction. AY minus mg cosine theta, right, is equal to minus m L over 2 alpha. And you guys are responsible to check my calculation that I haven't missed anything. So if it's correct, then let's simplify this guy. We have alpha, we calculated alpha before, right? If we substitute that, we are gonna get AY. So what was alpha? Let's move back. It is 3 over 2, and I have 1 here. So it's gonna be minus mg divided by 2 cosine theta. Okay, hope my calculation is correct. Now successfully we found AX and AY, except we need to be careful that the direction that we picked are wrong. The value are correct, but the direction that we showed on the diagram has to be in the opposite direction. But that's okay, we leave it as it is for the exam or for whatever you do in the future, because everybody understands that this negative means whatever I can see on the diagram is going to be in the opposite direction. And we care about the magnitude here. So if I have AX and AY, it means I can now calculate the total force A, which is AX squared plus AY squared. And obviously, I can then find the maximum because this is based on sine and cosine theta. And then based on the maximum, I can design this joint. I can calculate the stresses, and later in your 325 course, MEC 325, I guess you are taking it next year. In design course, when you design bearing, you need these values to design the bearing for these, because remember in this course, we just tell you that A is a joint, right? But in fact, it's a bearing, a ball bearing or roller bearing, and you guys need to learn how to design it. And when we say design for a bearing, because we don't actually design bearings, we just go to the tables and pick one bearing. Based on the forces that we have, I say, okay, my forces here is 1,000 Newton. So I look up the table and I see, oh, okay, I need this bearing. And then there are catalog, which we look catalog and we buy one bearing so it doesn't fail. Okay, so let's see if there is a question in the chat. So Joshua says, MEC 325 is not a very fun course. It's not, it's a design course. Or maybe I'm wrong, it's not 325. I guess it is 325, right, Josh? And somebody says, maybe I made a mistake in AY. Let me move back and check the calculation. No, because this is negative, Achilles, right? This is negative. And it goes there, becomes positive. So it is then plus. Everybody, let's double check our calculation. Let's first check the equation AY minus mg cosine theta, right? Because it has to be minus because it's in opposite direction of y. So the equation is correct. And if we put alpha, what is alpha? I might be wrong here. Oh, you're right. Alpha is 3 over 2 GL cosine theta. So Thank you, Akhilesh. So it is 3/2, right? G/L cosine theta. And so we have another 2 here. So it's going to be 3/4. So it's going to be 1/4 then. Okay, I just lost 1 point here in my exam. No, I'm just joking. So this is like some silly mistake that usually we do, but you need to be careful. The best way is not to rush it and substitute everything and carefully move these things to the other side and see it is positive and so on. I guess it's correct now, right? But everybody please double check to make sure it's correct. Are we good? Okay, that seems to be Cameron also is on the same page. Thank you, guys. Okay, with that note, if you guys don't have any other question for this, let's see what Josh says about 325. Oh, then that's too bad. They put a lot of formula in 325. So maybe in future when I teach 325, I make it one of the funnest course on the earth. I used to teach 325 long time ago. The good things about the teacher that have been in industry, like I've been in car manufacturer, then started a new job designing machineries for sawmills, is like for 10 years, 6 years in car manufacturer, 4 or 5 years in lumber manufacturing, and then designing machineries. Is when a course is about a design, so always try to relate it to some application. So rather than focusing on formula, so finding out, okay, if you want to, let's say, design a machine, each component, where you can buy them, how you can choose them, and so on, rather than too much formula. But anyway, for now, you guys, I guess, have to focus on the formula. That's unfortunate. So please study this problem carefully. It's many other problems that you will see in problem set 1 are very similar to this one. In fact, like there is one question that instead of a link, there is a plate which is being joined to the wall or to the ceiling, whatever. And we release it from rest. We want to find out AX and AY. Okay, when we release it. So in fact, this is exactly similar to what you've seen now, and you don't need to solve it for theta because the question is asked just at release. And you know at release, omega is 0, but alpha is not 0. And you have the weight and everything. So you can solve it, right? You just need to be careful that the rotation is a circular motion like that. And your AN and AT are going to be like that, right? AN and AT. So if this is, let's say the length is L1 and this is L2, then the radius here, you can calculate the radius. I guess this is one of the problem. Last year in the final exam, I guess the question was like a pendulum like this. And it has a center of gravity somewhere, G and theta, which we want to find out the reaction at A. Something like that, I guess. I post that maybe problem later on Canvas, so you will see. So anyway, my point is all these problems are similar, right? It's just a matter of knowing how to solve them and following this Euler's equation. And please practice this problem carefully. Okay, so let's get back to our lecture 24, which was last lecture, which now we continue as lecture 25 today. And it was a topic on energy. So again, to refresh your mind, we said we rely on this big formula here, which is the law of conservation of work and energy. It says whatever energy you have at point 1, you do some work on it and you get to point 2, this relation should hold. And I guess someone asked, it was maybe by email, that if we have friction, that's okay. Friction also is doing some work, but negative work, right? So it goes here. Friction goes here. Like you have a friction multiplied by the distance gives you the work, but with a negative sign, like it does negative work with negative sign. And as for energy, right, as for energy, we have TU and VE, which U is potential energy. We talk about it, it is mgh. And always for rigid body, consider the center of gravity. E is the elastic, 1/2 kx squared or kt theta 2, if it is, let's say, a torsional spring. And then the only things that left is the kinetic energy for a rigid body. Because for a particle, it's easy. If this particle has a speed, let's say v, in whatever direction it moves, right? Of course, it has to be tangent to the path at each moment. So simply T for us is 1/2 mv squared. But when it is rigid body, it may also rotate, which we can see on this path. If it is a car, you can imagine the car is changing its rotation if you're looking from the top. So we need to also consider its moment of inertia. So we can summarize the formula here. And in fact, it's super, super easy. So for each mass, if we break it down to little particles like this mi, and then we add all of those. So if it is a pure translation, then T will be simply 1/2 m v bar squared. Okay, whatever is the speed of the center of gravity. Like here we show it by v, but v bar. Nothing else. It's very similar to particles. Okay, it doesn't matter how big it is. If it is an airplane, but it's moving on a straight line without any maneuver or rotation, it's just its energy is 1/2 m v bar squared. What if it's fixed on a point like this point O, and it is pure rotation? What should we do now? So we know the speed of this little particle here is whatever distance it has, let's call it Ri omega. Then I can write down that the energy of this system is equal to, so for this particle is half of mi v2, like vi2, right? So which I can write it down as half of half of mi. Instead of vi, I write down ri omega squared. And I can simplify it as 1/2 mi ri omega squared. Oh, this is a square. So we know this guy has a definition. So do you remember from lecture 21 when we talk about mass moment of inertia? So the definition of mass moment of inertia was mass multiplied by its distance squared. So it means this guy here is I, moment of inertia for this little mass mi. Okay. Now, if I come and integral all of this or sum all of this, add all these little particles, what I will end up at the end is half of I-O omega squared. Okay, to summarize this, if we have pure rotation, simply the energy is half of I-O omega squared. So in future, you do not need to write like this mi and so on and add them. It was just to show you where it comes from. And simply, when you have pure rotation, your energy is half of I-O, moment of inertia about that point of rotation, omega squared. And scenario number 3 is combination of 1 and 2. Obviously, we can just add them. So T will be equal to half of m v bar squared plus half of, this time, be careful, it is I bar omega squared, because it's not rotating about a fixed point, right? It's rotating about its center of gravity. So 3 simple formula and easy to remember, and they are intuitive, right? And they are going to be very handy, and we're going to use them a lot. So take a moment to review these 3 equations and see if any part is not clear to you. So first one, obvious. It's just no rotation, pure translation. The second one, fixed on a point. And then the third one is combination of these 2. We add them, right? One comes from V bar and one comes from omega, rotation. So let's see them in action. For example 1. You want to find out the general formula to calculate kinetic energy for a rolling disk. Super, super easy. Try to solve it and then compare your solution with me. We have a disk and it's rolling without slipping. Try to think how it can be solved. Okay, interesting. My pen stopped working. Okay. Maybe I try again, draw a line. So we have the disk and this is on a fixed ground, and it's rolling with the speed omega, right? So this is omega. And we want to find out the energy, the kinetic energy T for this disk. Let's call the center O. And let's call this point C. Okay, I'm going to give you 1 minute to think about it and see how you can solve it. So this is scenario number 3, right? It rolls and also it moves. So it has two components. And you know its center of mass is here at point O. So try to use that formula and see what you will get. So this is the formula that we need. So T is equal to half of m v bar squared plus half of I bar omega squared. This is our general formula. And then tell me the number that you got. You can type it in the chat. That's a good point by Josh. Yeah, I agree, Josh. Sometimes if the content of a course is too much, then you have to rush through it. But sometimes, I guess, the teacher may have to cover all the topics because then in future courses, you need to know about something. But yeah, totally I agree. 3 to 5 is definitely a heavy course. Okay, anyone got a value here that we can type? You can type it in the chat. You just follow this formula, super simple, right? Maybe I will give you a hint. So you know the velocity of this guy. Right, V bar, which is R omega. R is the radius of this disk. And you know what is I bar for a disk, right? So any answer? No, let me then quickly solve it and then you can compare it. 1/2 m. So R omega squared plus half of I bar omega squared. Let's solve it first this way. If I substitute the values, I will get 1/2 m r squared omega squared plus 1/2. What is I bar for a disk? Half of m r squared omega squared. So I will get 3/2. Am I right? 1/2, 1/4. So somewhere So we have mr squared here, right? And we have 1/2. Okay, let's write it down then. 1/2. I'm factoring 1/2 and 3/2 mr squared omega 2. And the reason that I write it down like that, you will see in a moment. So I need just one more minute. Or you can write the whole equation like this. T is equal to 1/2 m r omega squared plus half of I bar omega squared. So the same things here. But this time, let's simplify it as like this. 1/2 and then mr squared plus I bar omega 2. Okay. And what is the definition of this guy? Again, remember the transformation of axis? Trans-axis. If you transform axis, so it means for you I bar plus mr squared, it means IC. So we could have write from the beginning is equal to 1/2 IC omega squared. And we know for a disk, if you again remember, IC we calculated before. Remember that gold, 10 kilogram gold disk in lecture 21, I believe, which we calculated IC, which was 3/2 mr squared. And as you can see, it's very, very similar to what we got over here. So the conclusion, if you have a disk that is rolling, and also, you know, it's category number 3, right? When it's rolling, also its center is moving, it has a speed, rather than writing like this general formula, you can, and you saw the proof here, right? You can simply write down that energy is equal to half of IC omega squared. And in fact, it is true because, again, do you guys remember from earlier lecture, we call this point something. Do you remember that? Center of instant center, right? It was an IC. And we said in instant center, we treat it more like a joint for a very short period of time. So if it is more like a joint, then we can simply follow the second formula that we had here. Second formula tells us if something is fixed to the ground at a joint, then you could simply use 1/2 IO omega squared, okay? And we say this is also true. So we are not violating anything. All the formula in the past or here, they confirm that for a disk rolling, this is the energy. And for you guys, we're almost done. Just to do a practice before the next lecture, solve the same problem using, this time, a ring. Let me draw it for you. And then you guys can work on it. And again, it is important, an important problem to know. So instead of a disk, now you have a ring, and then the ring is rolling, and your task is to find its a general formula for its energy. Okay, on Monday, first things, I'm going to ask you what is the formula for this. So this is O. Let's call this one C. And the mass of this guy is M. And the radius is R. And always remember, for a ring, when we talk about a ring, the radius that we are talking is the average radius. Okay? Not the outer radius, not the inner radius, the average radius. So we are done for today. Please review these topics. On Monday, I'm going to solve 2 problems which needs your attention. Example 2 and example 3. Example 3 is a cool example. Maybe you guys review these. So Monday, and even try to solve it. And then Monday, when I solve it, you compare with my solution. Okay? And also this ring, solve this ring as well. I guess in a few minutes, you guys have your tutorial, right? Please attend the tutorial and good luck with that. By the way, how's your tutorial going? Okay, I assume it's going well. Good, that's good. All right, guys, good luck with your tutorial. And also do not forget quiz 8 is this weekend, and it covers material, whatever we cover from Euler's to up to today's lecture, including the materials in today's lecture. But the focus will be on Euler's equation and on gyroscopic moment, like lecture 21, 22, 23, and 24. Okay, if there is no question, then let me stop recording.